by using hybrid orbitals. And so what we do then is we know we need to explain linear, trigonal planar, tetrahedral, and these guys as well, but less important for us, shapes. And to be linear, you have to have 2 equivalent orbitals. To be trigonal planar, you need to have 3 equivalent orbitals, right, for sigma bonds or lone pairs. Tetrahedral, you need to have 4 equivalent orbitals for sigma bonds or lone pairs, just like in methane. And so this is what we do, and we'll go through the explanations of these things. But if I take an S and 3 Ps, right, my S and 3 P orbitals, oh yeah, this should be the different orientations, but I can mix them, right? If I take 4 atomic orbitals, I have to get 4 hybrid orbitals out of it. Right? And it turns out when you mix them equally, so each one of them is going to be 3/4 P and 1/4 S, right? If I split him 4 ways, everybody gets a quarter. And so, you know, the way they draw it is something like this. These are all supposed to be the same now. So now these are all 4 equivalent orbitals that are all 25% S and 75% P. Okay, and what happens when you put 4 equivalent orbitals around something, right? With Vesper predicts that they're going to try to get away from each other as far as possible, and what you get is the tetrahedral shape. And says this is going to explain methane. So we're going to hybridize carbon to tetrahedral. We're going to get carbon in the center, 4 equivalent sp3 hybridized orbitals, and then these will be the s orbitals for H. So here I've just drawn 4 sigma bonds. All right, so I'm going to basically say the same things now a bunch of times. On the one hand, some people don't like this idea of hybridization. It doesn't really make sense. So if you're one of those people, have a think on it. But ultimately, it's a model that works to explain shapes. So if you follow the rules, you can kind of talk about it. So what we're going to do for hybridization, we're going to mix non-equivalent atomic orbitals, right? Mixing S's and P's mostly. And we're going to get different shapes from the original orbitals, right? We'll start with S's and P's, which looks like spheres and peanuts, and we're going to get our sp, sp2, and sp3 hybridized orbitals out of that. The number of hybrid orbitals is equal to the number of pure atomic orbitals, just like I said. So if I take 4 atomic orbitals, an s and 3 p's, I have to get 4 hybrid orbitals. Covalent bonds are formed, just like in valence bond theory, by the overlap of hybrid orbitals with atomic orbitals or hybrid orbitals with other hybrid orbitals. All right, if we take an s and a p, we get 2 equivalent sp hybridized orbitals. 2 hybridized orbitals will adopt this linear shape. Right, they'll try to get away from each other like this. We'll have a bond 80 of 180 degrees. If we take an S and 2 P's, that's 3 atomic orbitals. I have to get 3 hybridized orbitals, sp2, and 3 equivalent orbitals take this shape. If I look from the top, what would it look like? Just from straight up, it would look like this, and this bond angle would be 120 degrees. This is trigonal planar. And as we just saw, 4 atomic orbitals, right, an S and 3 P's gives me 4 hybrid orbitals, sp3 hybridized orbitals, and that adopts the tetrahedral shape with the bond angle of 109.5. These are all good bond angles to know. All right, I kind of drew a picture there already. So again, we're looking at the same thing. This is another slide just showing you the explanation of how s orbitals and p orbitals would get mixed up. They hybridize to form S and 3 P's, hybridized to form 4 equivalent sp3 hybridized orbitals. And you can see the way they're named. If you're made from 1 S and 3 P's, you're called sp3. If I put these 4 equivalent hybridized orbitals together, I get the tetrahedral shape, like this. And so in methane, you can see that if I have my H atoms with their 1s orbitals, I form then, that's probably a mistake, but I'm getting the color, forms 4 equivalent sigma bonds. What's the difference between methane, CH4, and ammonia, NH3? We got a lone pair, so now what's in one of those orbitals? So we still have our tetrahedral geometry, HHH, but instead of forming a sigma bond in that guy, we have a lone pair. So lone pairs of electrons can exist in hybrid orbitals. And we knew this. Interestingly, the bond angle here is 106.7. That's less than 109.5 degrees, right? Remember, Vesper predicts that because this lone pair can sort of expand a little bit, it pushes these guys down and makes this bond angle smaller. All right. If we look at sp2 hybridization, we take an S and two P's, hybridize them to get 3 hybridized orbitals, 3 equivalent sp2 hybridized orbitals. When you put those together, you get this shape, right? So from the top, I would draw it like this, just so you, later on when I draw these things, you'll understand how it's supposed to be in this picture. That is trigonal planar. All right, I can also draw it from the side like this. So these pictures are equivalent, right? I'm either looking at the side or from the top. And here, what do we see here? We're seeing boron, fluorine, sigma bonds being formed by the direct overlap of sp3 hybridized orbitals and what kind of orbital on F? That's a P. Nice. sp hybridization gives us linear geometry. So I take an S and a P, right? That's 2 atomic orbitals. I need to get 2 equivalent hybridized orbitals. If you put 2 things together, they adopt a linear geometry. And so I draw it like this. All right, this is linear, 180 degrees. Right here we see sigma bonds between chlorine P orbitals and beryllium sp hybridized orbitals. And we've seen this before, but sigma bonds, right, are the direct overlap of electrons. The electrons are on the axis of between the atoms. So if the atoms are like this, and they are, you can see that the electron density is here and here. It's between the atoms. These are called sigma bonds. And they can be formed, as we've seen, from S's overlapping, from S's and P's overlapping, or from P's and P's overlapping, or any hybrid, right? sp3 can overlap with any of them. So I could draw, this is what shape, or hybridization is sp3 tetrahedral. It could form another bond. Whoa, bad drawing by me. This is supposed to be another sp3 hybridized atom. And you can see I've shown the direct overlap of sp3, which is a sigma bond between hybridized orbitals. So we can mix and match all those different orbitals overlapping to give us sigma bonds, as long as they overlap directly. Here we got the same thing again, right? A summary. So how do I make sp3 hybridized orbitals? I mix an S and 3 P's. And what you get are 4 equivalent sp3 hybridized orbitals. The shape adopted is tetrahedral. If I take an S and 2 P's, I get sp2 hybridized orbitals, and they're trigonal planar. S and a P gives me 2 equivalent sp hybridized orbitals. And we could also add some D's to get some other shapes, right? Trigonal bipyramidal and octahedral.